So I'm going to talk about radio astronomy and black holes and some astrophysics in the kitchen. And you can see my title is in Rhodes purple. That's because a lot of this is done with engagement from Rhodes researchers, which you will hear about in due course. So for starters, let me tell you what radio astronomy is, right? Normally, when I say astronomy, people think of something like the picture on the left here, right? A starry sky, the Milky Way, stars, and a telescope used to gaze at them. And indeed, this is how astronomy was born. So astronomy was born as the study of the universe in what we call optical visible light. But in fact, optical light is just electromagnetic radiation, just like radio. And optical light is radiation within a fairly narrow range of wavelengths. And electromagnetic radiation actually comes in a much wider range of wavelengths, but very few of them reach us on the ground here. So this picture here is a very handy illustration of how deep different wavelengths penetrate into the atmosphere. And you can see that only wavelengths that make it all the way to the bottom are visible light, this narrow little band here. And then there's this huge, huge band of radio waves, which also makes its way to the bottom, to the Earth. So if the universe is showing us something in radio waves, then from the surface of the ground, we should be able to see it. And maybe one question I should answer straight away, it's the why look question. And there's this question that I get sometimes, you know, why should, especially a country like South Africa, why should a country like South Africa bother building telescopes when it still needs more schools and more hospitals? And of course, the general answer to that is, you know, a healthy society actually needs both. And what astronomy does, well, you know, to understand the universe, that's been a basic human need since the first hunter-gatherers looked up at the sky. So in a sense, astronomy serves that need, but also just doing astronomy because it's challenging, because it's super challenging. What it does for you, it creates a pool of skilled people in your country who are extremely good at solving complicated technical problems. And there are some examples of that. So for example, Wi-Fi was invented by a radio astronomer who was working on an unrelated challenging problem. So, you know, you are listening to me talk right now, and that's mostly thanks to work by this guy, John O'Sullivan. Another far more recent example is this news headline here. So just now with the COVID epidemic, the government has actually asked our observatory to manage the development of ventilators. And that's because if you're good at building radio telescopes, which are just about the most complicated machines you can imagine, you're also going to be very good at building other machines. So that's the why of it. And like I said, the radio window is much wider than the optical window, and potentially it can give us a completely different window on the universe. So you would fully expect astronomers to trip over themselves to explore the radio window, you know, as soon as radio waves were discovered, like around 1900s. You know, they should have been trampling all over themselves to look in the radio window. In fact, they did no such thing. And well, there's a reason for that. Nobody actually expected the radio window to show anything much. And even the smartest scientists wear blinkers, including today. And the reason people didn't expect to see much in the radio window, well, I'm going to give you your first lesson in astrophysics now. What is this? Is this an annotation suddenly? Let me see if I can get rid of it. Does anyone know how to get rid of annotations? Yeah. Clear. Yeah, I cleared it.
Well done.
Okay, so I'm going to give you your first lesson in astrophysics. Now, when I was young in school, I thought an astrophysicist was something extremely glamorous, and that astrophysicists had to be at least twice as smart as regular physicists or any other scientists. And eventually I failed to become one, but I did change my mind about them. They are bluffing a little bit. In fact, quite a lot of astrophysics is just normal regular physics, it's just physics of very large things. Some of it is pretty weird. We're going to see some very weird astrophysics later in this talk, but a lot of it is very conventional physics. And a lot of regular physics is just common sense. So I'll give you an example here. I would like to see if you can spot the connection between these three pictures. And the connection is not that we like to braai all sorts of different animals in South Africa, no. The connection, in fact, is that the sun, an oven, and coals on the braai, they all emit light in the same way. And this is something that's called black body radiation in physics. It's kind of a confusing term because it's not, the sun is not black at all. But in physics, when we call something an ideal black body, it's something that completely absorbs all radiation. So a lump of coal on the braai or a ball of hot gas like the sun is pretty close to an ideal black body. And the disco ball wouldn't be a black body at all. And now the thing about black bodies is that if it's heated up to a certain temperature, it's going to emit thermal radiation. And that radiation is going to come at all wavelengths, and it just comes from the heat of the body that's been heated up. But this radiation is very, very predictable. Its spectrum is very predictable. It just follows this nice little curve like this. And in fact, from the outside, you don't even care what the source of the energy in the black body is. So for the sun, for the oven, and for the braai coal, you have very different sources of energy, very different reasons why these objects are hot. A braai coal is hot because it was burning. An oven is hot because there's an electrical coil inside it heating it up. And the sun is hot because there's thermonuclear reaction going on. But if you look at this object from the outside, the sun just looks like a very, very hot braai coal. And its spectrum is exactly the same. And turns out that this kind of radiation, this thermal radiation from the stars, it peaks, it gives you a peak in the visible wavelengths. And that's sort of actually not a coincidence at all. I mean, the reason our eyes see in the visible wavelengths is that because that's where the most light available on the Earth is. It would be a lot of fun if we had eyes that could see in the radio, but because there's no natural radio on the surface of the Earth, they wouldn't be very useful. So we did not evolve eyes that see in the radio, we evolved eyes that see in the visible spectrum here. And in the 1900s, astrophysicists didn't really know any other sources of radiation. They kind of assumed that you've got the sun, and the sun emits as a black body according to this curve. And then you've got the galaxies, and the galaxies are composed of stars, and so they're also going to emit according to this curve. And if you look on this curve, this acts as wavelength. So radio is all the way over here on the right. So a black body will emit a certain amount of radio waves, but a very small one, and they're not particularly interesting. And you might be able to detect them from the sun, but you certainly wouldn't be able to detect them from even the nearest star. It would be too far away to see any thermal radio from the star. So anyway, that's what astronomers thought in 1900 when radio waves were discovered. And that's why no one really thought to look in radio at anything from the universe. And it actually fell to an engineer to discover this. So this is a guy named Karl Jansky, and he was a radio engineer, and he was actually employed by Bell Labs to help with developing radio communications. So radio had been invented. They were now trying to develop it as a tool for transatlantic communication. And what they were finding was there were lots of sources of interference, static, like hiss. I'm sure you've heard that on the radio. That was interfering with communication, so Bell Labs wanted to figure out where the static was coming from. And so they hired this guy, Jansky, and gave him the job. They said, okay, figure out where static comes from. And what he did was he built this contraption, and they called it Jansky's merry-go-round. It's a directional antenna, which receives signals from a preferred direction. It's on wheels on this little round platform. And then what he did was he would turn this thing around and point it in various directions and see if he could find static. He literally had a set of headphones plugged into it. So he was trying to figure out which direction static was coming from. And one of the first things he discovered was that static comes from thunderstorms, for example. He figured that out pretty quickly. But then there was another noise, there was another recurring hiss that he kept hearing, and he was hearing it pretty much daily. So because it was daily, at first he thought it was coming from the sun, but then he realized, he timed it carefully, and he realized that it doesn't come every 24 hours. It actually comes every 23 hours and 56 minutes. And that's very important. That's a bit of a giveaway. So if you're not an astronomer, I'm going to take 4 minutes out of your day for the rest of your life. If you're not an astronomer, and if I ask you how long does it take for the Earth to rotate once around its axis, most people would probably say 24 hours, right? In fact, that's not quite true. It takes the Earth 23 hours and 56 minutes to rotate around once. So if you were to fix your gaze on a star somewhere infinitely far away, you would see that it takes 23 hours and 56 minutes for that star to come back to the same position in the sky. And that's what we call a sidereal day. A sidereal day is a star day. Now for the sun, because the Earth is moving along its orbit while it's rotating, for the sun, it has to rotate a little bit extra for the sun to come back to the same position. And that little bit extra is the 4 minutes that makes it 24 hours. So basically a solar day is 4 minutes longer. But the implication of this is that if you see a signal that repeats not every 24 hours, but every 23 hours and 56 minutes, then you know that that signal has to be coming from the stars somewhere. It's not going to be local to the solar system. It's definitely coming from very far away. So Jansky, once Jansky timed this and once he read about the sidereal day, he realized that he was actually receiving signal from outer space. And eventually he concluded that this noise was coming from the Milky Way, from our galaxy, and that it was strongest towards the center of the galaxy. And you would think this would be a very big deal, right? It was reported in the press, and it was a huge deal because, as I just explained to you in the previous slide, there wasn't supposed to be any radio signal coming from stars or galaxies. And suddenly there's this big booming signal that Jansky detects, and there's nothing in astrophysics that can explain this signal. So you would think it would be a pretty big deal for astronomers, but in fact it wasn't. Everybody just went, whatever. Completely ignored the result, didn't do anything about it, and even worse, his employer didn't care. Bell Labs said, well, that's very interesting, but we're not paying you to detect cosmic noise, get back to doing radio. And so he stopped work on this. And there's kind of a sad postscriptum to this. He died in 1950, just before radio astronomy really took off. So he never got to see what he discovered, really. But he does have a unit named after him right now, the Jansky. It's a unit in radio astronomy, which is pretty special because there are lots of people have Nobel Prizes, but very few people have actual units named after them. So anyway, like I said, astronomers ignored Jansky pretty much, but there was one guy that didn't, and it was this fellow, Grote Reber. And this guy was truly extraordinary. I mean, it's mind-boggling what he did. He was not an astronomer. He was a radio engineer. But he read about Jansky's discovery, and he realized, okay, this is important, and I want to look at this. So he basically set out to build his own radio telescope. And that's easily said, but I mean, no one had even thought of radio telescopes at the time. The concept didn't exist. There wasn't anyone to tell him how to build a radio telescope. So he basically had to sit down and invent from scratch, well, what do I need to receive radio from the universe? What should it look like? And remarkably, so he built this 9-meter thing in his backyard. Quite remarkably, a lot of the design decisions he took were, it's been more than 80 years since, and we're still building radio telescopes the same way. So he came up with the concept of a dish. He came out with the concept of a feed. He came up with the concept of a changeable feed. He did all that, and he did it in his mother's backyard. So really quite a remarkable guy. And he was the first person to systematically study radio emission. And he made these maps. So these maps are actually maps of radio emission from the entire sky. And here you can see the center of the galaxy. Here you can see some other sources. I'll get to them shortly. So he quite systematically took his dish and he moved it around the sky and he recorded the signals and he came up with these maps. And he published them in 1937. And again, not much happened. Astronomers pretty much ignored it. And then from the timeline, you can probably guess what happened next. Next, World War II happened. So people kind of stopped worrying about cosmic noise, and detecting aircraft noise was suddenly a lot more important. So a lot of human ingenuity went into building devices for detecting incoming aircraft. And some of these looked pretty silly, like this, and like this. There were actual people on the beach listening for aircraft with these things. So that was all very inventive, but there was one contraption invented just shortly before the war, which proved even more efficient at detecting aircraft, and that's radar, right? And radar we still use today. Some of you probably have an idea of how it works. Radar is actually an acronym. It stands for radio, direction, and ranging. And the way it works is you have a radio dish and you send out a very powerful signal, and some of that signal is reflected off the airplane and comes back at you. So if you measure this faint reflection, you can detect where the aircraft is. And this proved to be very successful in the war, and a lot of work was put into it. And this is what really incubated a boom in radio astronomy afterwards. Because if you look at the radar, okay, never mind transmitting signal, but the second part of the problem, how to detect the faint reflection, how to detect the signal, that's basically the same problem you're trying to solve in radio astronomy. So all these young guys who the army drafted in and put them in temporary steel buildings and told them to develop radar, they learned to solve all sorts of technical problems very quickly. And, it's very motivational to solve problems when the problem is a German bomber with actual bombs coming at you. It gives you a lot more motivation. If you think finishing a PhD is pressure, try detecting enemy bombers. Now that's pressure. So these guys learned to solve a lot of problems under pressure and to solve them quickly. And when the war ended, a lot of them became radio astronomers. And the reason I'm showing a light bulb here is just to remind myself to tell you that the signals that we detect in radio astronomy are actually extraordinarily faint. So if you took all the energy collected by radio telescopes since radio astronomy began, if you took all that energy, it would be just about enough to power a light bulb for something like, I forget, it was either half a second or 20 seconds, but not very long at all. So to do radio astronomy, you need to be good at picking up extreme faint signals. And this technology was developed very actively during the war. And another important thing, and this is illustrated with Grote Reber's maps. A very important thing if you're looking at the sky is resolution. So a radio map is actually like a black and white photograph, right? A radio map, a black and white photograph shows you white spots where something is bright and dark spots where something is not bright, right? It shows you the intensity of the light in the photograph. A radio map is the same way, but it shows you the intensity of the radio in a particular direction. So a radio dish is like a camera, except it's a camera with only a single pixel, because you point it in one particular direction and you record the intensity. So having a single pixel, well, it's not necessarily so bad because you can scan your pixel across the sky to make an image. If your subject is sitting still, and the sky is generally sitting still for us, a single pixel is okay. You can scan it and you can make a full image. But the problem is, how big is your pixel, right? If you want to make out fine details, then the size of your pixel is quite a fundamental limit. And this applies to everything, actually. This applies to radio dishes, this applies to telephone cameras, this applies to your eye, this applies to the Hubble Space Telescope. Everything has a resolution limit. How small can you make your pixel? How small are the details that you can distinguish? And this is where the numbers work against radio astronomy, because this pixel size is given by the ratio of wavelength to the diameter of your aperture. So the wavelength of visible light is less than 1/1,000,000th of a meter. And the wavelength of radio is centimeters to meters. The size of an aperture for your eye or for a phone camera is millimeters. And the size of an aperture for an optical telescope is meters. And for a radio dish, it's also meters and tens of meters. But you can see that these numbers don't really work in favor of radio telescopes. So radio dishes actually suffer from relatively poor resolution. In fact, it's so poor that if you work out, if you've got a 25-meter radio dish that's observing at 21 centimeters, a famous wavelength, your pixel is going to be about the size of the moon, half a degree. So as you can imagine, you're not going to make out a lot of detail if your single pixel is as big as the moon. By comparison, the human eye, well, you can certainly tell the human eye can do better, because when you look at the moon, you can make out details. And the definition of 20/20 vision is a resolution of 1 arc minute, so that's about 30 times better than a radio telescope. But that's nothing compared to what optical telescopes can do. So the Hubble Space Telescope, for example, has a resolution of 0.05 arc seconds, and that's about the size of a 5-rand coin at 100 kilometers. Right? That's very high, that's superb resolution. It's very hard for radio telescopes to compete with this. And in fact, well, how would you compete? The obvious thing is to try to build a bigger dish. You can try to increase D, but this is complicated, and 100 meters has been sort of the practical limit for fully steerable dishes. So this here is a picture of a 100-meter dish, and it's quite hard actually to appreciate its photo in its scale in the picture. But just imagine a football field. This dish is the same size as a football field, and it's mounted to be fully steerable, right? It can tilt and can swing around. So this is very complicated engineering, and unfortunately one day they woke up and went out and realized it had fallen down, which was a very unpleasant surprise. And this is what the news made of this, proving that fake news is nothing new. So it's very difficult to build a dish over 100 meters. Another thing you can do, you can find a convenient hole in the ground. So if you've got a depression in the ground that's the right shape, you can build your dish in the hole. And that's something that's been done for a telescope called Arecibo in the United States. And there's a brand new telescope called FAST in China, which uses the same principle. So they found a geological feature called karst sinkholes. I don't know if there's any geologists in the audience, but they would recognize this. And karst sinkholes have just the right shape to put a dish into them. So they look like this from there. And the reason I've got James Bond in here is because this telescope actually appeared in a James Bond movie. At some point, they climb out and clamber over this dish. But it wasn't a very good James Bond movie, so you probably don't remember. So basically, 300 meters, 500 meters is about as big as you can make it. And also, you're kind of stuck pointing straight up if you build a dish like that. You can sort of move this receiver box around a little bit and point a little bit off vertical, but it's not very flexible, right? You're looking pretty much in one direction, and you have to wait for something interesting to come overhead before you can observe it. So that's not very good, but turns out there's other solutions to the resolution problem. And the solution, well, the actual solution dates back to 1801. And in 1801, Thomas Young conducted a famous physics experiment. It was called the Double-slit Experiment. And what he was trying to do, he was trying to demonstrate the wave-like nature of light. So the way his experiment was designed, this is actually the drawing from his original paper, but it's better illustrated here. So he had a screen with a slit, and that screen was illuminated by sunlight. And that slit illuminated the second screen with two slits. And then what happened was those two slits essentially gave you two copies of the same light wave. And those two copies of the same light wave propagated onto the screen here, and they gave you a pattern of dark and bright stripes on the screen. And the reason that pattern happens, you can sort of, I guess, follow it in this animation, because in some spots on the screen, the two waves come together in unison, and so they give you a signal. And in other spots on the screen, the two waves from the two splits come in opposite phases, and they actually destruct. So on some parts of the screen, you're building up signal. On other parts of the screen, you're building up no signal at all. And this would only be possible if light was a wave. So his experiment proved that light behaved like a wave. But turns out there's other uses you can put this principle to, and that's called an interferometer. So as a mental experiment, we can take the same setup that Thomas Young had with the screen and the slits, and now we're going to reverse the direction in which light travels. This is something you can always do in physics. You know, the laws of physics are symmetrical. You can change signs, you can change directions. So if you put a little light bulb on the screen here, and if you have waves propagate from the light bulb to the two slits, and then from the slits over here, and then we look through here, what are we going to see, right? We should see something very similar. What in fact we're going to see is that if we put the light bulb where a bright spot was, we're going to see the light bulb through the slit. And if you put the light bulb on a dark spot, we're not going to see anything, because the waves from the light bulb are going to cancel each other out when they get to the slit here. So by moving the light bulb up and down here, we can change the signal at the slit here where our eyes receive this. And this is called an interferometer. You can also do it on the radio. In fact, it's even easier to do it on the radio for different reasons. So this is this picture shows the same thing, except the back screen is now the sky. So now we have a source of radiation sending us a wave from the sky, and that wave hits two antennas. And then we take the signal from those two antennas and we mix it together and we measure it, something like a voltmeter. And when we do that, this black and white pattern on the sky, you know, there isn't actually a black and white pattern in the sky, right? It's a mathematical representation of the sensitivity of our telescope. So if we had a radio source where a dark stripe is, we would see nothing on the voltmeter. And if you had the radio source where a white stripe is, we would see a signal. And the trick here is that the spacing between these stripes, what we call fringes, the spacing of the fringes is given by lambda over b, where b is the baseline, the distance between the two antennas. And baselines can be made quite large, right? There's absolutely no problem at all in taking two small antennas and setting them 100 meters apart, or 1,000 meters apart, or 8 kilometers apart. Technically, it's pretty simple. But by using the baseline, by using the fringes, suddenly you have this capability to distinguish far more smaller features given by a size of lambda over b compared to the pixel that your dish gives you, given by lambda over d. So a dish pixel would be something large here, large and coarse, but with the fringe, you can suddenly detect small details. So this way you kind of beat the resolution conundrum with the radio telescope. And if you cleverly combine signals, you can do all sorts of wonderful things. And one of the first experiments of this kind was actually done directly after the war, again by people who were involved in radar during the war. And they figured out how to do this trick, not with two dishes, but with one dish. And that's because they realized that if you have one antenna up on a cliff, and there's a source of radiation coming in at an angle like this, some of the radiation is going to come to the antenna directly, and some of the radiation is going to bounce off the sea and come into the antenna from this direction. And that's exactly the same thing as if it didn't bounce off, but rather went on this way and was received by a second antenna here. So you're kind of creating a virtual antenna by this reflection of the sea. And this sounds very clever, but in fact, they already knew about this effect during the war. And during the war, when you were doing radar, it was a nuisance. Because imagine if that's your radar dish and you're trying to track that enemy bomber. So you're trying to keep this bomber in your pixel because you want to know where it is. And instead, because of this interferometer effect, you get a pattern of stripes across your pixel, and the enemy aircraft keeps disappearing because it's going into a black stripe and then coming out in a white stripe. So for radar, that was a very big nuisance. But once the war ended and they started thinking about what else they can do, they suddenly realized, wait a minute, this can actually be quite useful for astronomy. And how they applied it to astronomy, they actually went and proved that bursts of radio from the sun are associated with sunspots. And these are the drawings they made for their papers. So the disk here is the sun. This is the horizon. This is the sun rising. And these are sunspots. And the horizontal lines are the fringes of their interferometer. So as the sun rose, the sunspots went over the fringes, so the signal they received went up and down, up and down, up and down. And this was proof that sunspots, that the signal was actually coming from sunspots and not the whole sun. Because if it was coming from the whole sun, they wouldn't see this effect. It would be kind of averaged out and washed out. So that was the first experiment in radio interferometry. And at the same time, something else happened. You remember I told you it was a mystery for Karl Jansky and for everyone else where the radio signal was coming from, because there was no physical mechanism that could produce radio emission. Astrophysicists couldn't think of one. Well, by the 1950s they could. So in the early 50s, theoreticians proposed a mechanism that explained galactic radio emission. And this mechanism is called synchrotron. And this happens when you've got a charged particle, such as an electron, accelerated, in this case by a magnetic field. So it turns out that our galaxy is bathed in relativistic, very fast traveling electrons, also called cosmic rays. And these things zip around the galaxy and they spiral around the magnetic field lines of the galaxy. And as they spiral, they emit radio waves. And well, the obvious question then is, where are these speedy electrons coming from? Well, they're coming from extremely high energy events. So for example, supernova. I'm going to talk about supernova a bit later when I get to black holes. But basically, this radio emission is a signature of something that's actually super, super energetic, despite the fact that radio emission itself is very faint. So this was really a new window into the universe. You can kind of think of, before radio, the universe was like Christmas lights to astronomers, because you had stars, you had galaxies, everything was burning fairly steadily, nothing particularly spectacular was going on. And suddenly, when you can see in the radio, suddenly you can see all these fireworks. You've got like electrons zipping around and whatnot. And that's going to be a recurring theme. Radio astronomy is all about detecting the fireworks. We really see the most energetic things in the universe on the radio. And of course, there were other fireworks surrounding this discovery of synchrotron. Turns out that at least 8 different people sort of thought they discovered it. And in the end, all 8 of them stopped speaking to each other. But yeah, this sort of thing I'm sure you see in other sciences as well. So anyway, that was the 50s. We discovered the mechanism of radiation, and then there was some very clever mathematics that people developed. They basically figured out how to put everything together and how to put many antennas together and make images of the sky with a resolution, with a pixel that's given by the longest baseline. And this technique is called Aperture Synthesis. Funnily enough, when they first discovered it, they couldn't do it because computers weren't fast enough to make the calculations. But by the 1960s, computers got fast enough, and people actually started doing this. And the first telescope to do aperture synthesis was the 1 mile telescope at Cambridge. And eventually that led to a Nobel Prize for this guy, for Sir Martin Ryle. He was yet another World War II radar person. And from then on, radio astronomy just took off and never looked back. So I'm going to talk about 2 modern aspects of radio telescopes. So given all these developments, there are 2 ways in which you can push radio telescopes today. Well, there are actually many others. I don't have time to speak about all of them. I'm just going to concentrate on 2. One thing you can do, you can build what's called a compact array. So you take many, many dishes and you put them together in more or less the same location, and you tie them together and you have them operate together. And what you get then, you get superb sensitivity and you get superb imaging quality. You get like a radio camera that gives you fantastic images. And I'm going to show that to you in a second. And examples of this are the Very Large Array in the United States. They've got 27 dishes, which go out to a maximum of 36 kilometers. Another example is our very own MeerKAT in the Karoo, just recently completed. That has 64 dishes and 8-kilometer baseline. But there is an extension in the works being built together with the Germans, and we're going to get 20 more dishes, and the baseline is going to increase. And the future Square Kilometre Array, by 2025, we're supposed to have 197 dishes in the crew with a max baseline of 120 kilometers. That's in the future. In the meantime, there's another direction into which you can push this technology. You can do something called very long baseline interferometry. So you can take telescopes across the world and you can pull them together and make them work together on an ad hoc basis. And for technical reasons, you can only do this with relatively few telescopes at a time, but then you get fantastically long baselines, intercontinental baselines, thousands of kilometers. And remember, the longer your baseline, the finer your pixels. So you can have absolutely incredible resolution with VLBI. You can even put a dish in space. People have done that. This is a highly specialized technique, but it does give you extremely high resolution images. And an example of this that was in the news last year is the Event Horizon telescope, which produced this actual image of a black hole. And I'm going to talk about this image a little bit later. This was really a spectacular achievement. And then, of course, in the future, in some distant future, we are going to have the full Square Kilometre Array. And that's actually going to combine the best of both. It's going to have a compact core, which will make fantastic images. And it's going to have very long baselines, which will give us fantastic resolution. So that's the two kinds of telescopes I'll talk about. MeerKAT first. This is an actual aerial view of MeerKAT. MeerKAT consists of 64 of these dishes, 13.5 meters each. They're spread over up to a maximum distance of 8 kilometers. And it really is the best imaging machine of its kind right now, really without a doubt, and completely a South African product. And of course, it's the product of a very large team, but in many respects, this machine is also the brainchild of Professor Justin Jonas, who many of you might know at Rhodes. So he basically came up with a lot of the concepts that are behind this telescope. And like I said, it's a fantastic imaging machine, and you might have seen this picture in the news. This was the inaugural MeerKAT image back in 2018. And this is an image of the center of our galaxy. Now remember, radio shows fireworks, so we're actually seeing fireworks at the center of the galaxy. And in here is a supermassive black hole. I also like to show this image in, just to illustrate. So the galactic center was actually already detected by Reber. So if you look at that original map made by Grote Reber, the galactic center is this blob here, all right? And for reference, the size of the image is about this, right? If you want to compare it to a full moon, this is about 2 moons across. So it's really a fairly small patch of the sky. I like to show this image in this version because this shows the person responsible for producing it. He is actually a visiting professor at Rhodes as well. And then there's this version of the image, which is also highly amusing because I have never seen a president in front of an astronomical image, and suddenly we've got 2 at once here. But one thing this image illustrates, and this is another bonus of looking in the radio window, if you look at our galaxy, and this here is obviously an artist's representation of our galaxy because we live in it. We would not be able to look at it straight down like that. But if you look at it schematically, it looks like this. You've got the center here, you've got these spiral arms, and the sun is over here. So it's kind of a little bit peripheral. We're not central to the galaxy at all. We sit here. And we know our galaxy looks like this because we see many other galaxies in the sky. And this, for example, is a Hubble Space Telescope image of a classical spiral galaxy, which is very, very like ours. And the thing to realize is that the relative dimensions of the galaxy are like an LP record, if you still remember what LP records are. So it's a disk, and it's about as flat as an LP record. It's really, really a very flat disk. And if you want to imagine our galaxy, so imagine an LP record that's not made of vinyl. Imagine it's made of glass, and we sit somewhere here in the LP record, and we're trying to look through the glass towards the galactic center. Now, if we wanted to look out of the disk, that's easy because the disk is thin. So looking in other directions, we don't have a lot of glass to look through. But if you look towards the center of the galaxy, we see something like this. This is the plane of the disk, and you will see all these dark smudges here. This is dust. This is interstellar dust that sits in the galaxy. And the dust basically means that your glass disk is not quite clear glass. It's a little bit dusty. So if you want to see from here to the center of the galaxy, there is a lot of dust in between, and you're not actually going to see very much in the optical. But in the radio doesn't care about dust. It passes right through it as if it wasn't there. So in the radio, you get to see the center of the galaxy in all its glory. And people, of course, have looked before MeerKAT. So this image kind of shows off the increased capabilities that MeerKAT has compared to the competition. These were the older images of the center of the galaxy made by the VLA and the GBT. And this again is the MeerKAT image. So you can see the improvement in detail and in sensitivity is just absolutely fantastic. And like I said, all of this is fireworks. So all of the radiation you see, this is all energetic electrons that are zipping around and doing stuff. And there's a lot of stuff happening around the black hole. Well, since I mentioned black holes, I might as well get into black holes. That was going to be my next subject. What you might not realize is that in this image, there are actually different kinds of black holes already present. And one of these over here is a fairly small black hole. It's only a few solar masses. This symbol we use in astronomy, it's called M solar. It's the mass of the sun. So this is a relatively small black hole here. It's about the mass of the sun. You don't see the black hole, of course. What you see is the fireworks of the stuff around it. And then there's a much larger black hole at the center of the galaxy here, and this one I'll talk about later. So where do small black holes come from? Here's another little image of it's a cutout from the same image of the center of the galaxy. It illustrates one thing very nicely. So massive stars live fast and die very young. The more massive a star is, the shorter its lifetime. And when a massive star dies, it literally goes out with a bang. So what happens is a massive star explodes in something called a supernova. And nova, of course, comes from new. Historically, they were called this way because when a supernova explodes, you literally see a new star in the sky. The original star might have been too far away and too faint for you to see. But when the explosion happens, suddenly for a few weeks, there's a new star on the sky. So that's a supernova. And when it explodes, what's left behind? It explodes, it saturates the surroundings with these speedy electrons that we talked about earlier that give the synchrotron radiation. And it also leaves a remnant. So the outer envelope of the star blows up and blows away. And the remnant is going to be either a rapidly spinning neutron star called the pulsar, and these fascinating things, but I don't have much time to talk about them. Or if it was slightly bigger, it collapses into a black hole. And this image here is actually, it's a wonderful illustration of, it's almost astrophysics like a cartoon, because this is a star that went supernova fairly recently by galactic standards. And you can see it just perfectly, you can see this is the explosion broadcasting out. And this is what's left of the star. Because the explosion was slightly asymmetric, the star actually gets kicked out. So it's going zoom out of, it used to be here at the center, but now it's getting the hell out of there. And there's just an explosion and it's missed. And this, quite fittingly, this is called the Mouse Nebula. And, I think to me it looks like a Tom and Jerry cartoon, so the mouse name is appropriate. So this leaves behind a black hole, and I'll get to black holes in a second. I just wanted to show that once you know what to look for, these kinds of clouds, once you look at the center of the galaxy, you can actually see that there's these kinds of clouds everywhere. So there's been stars exploding all over the place here. And that's actually not surprising because there is a lot of matter at the center of the galaxy. There's a lot of stuff going on, and that means there's a lot of star formation. So stars are constantly being formed. New giant stars are being formed, and they live quickly, they explode. And today we're seeing the aftermath of these explosions. So like I said, three kinds of black holes. You can see here. So there's a black hole that was left over from a star. And then there's these kinds of black holes. And these are kind of mysterious, but it's fairly conventionally accepted now that at the center of every galaxy is a supermassive black hole. The black hole at the center of our galaxy is about 4 million solar masses. It's not quite clear how these black holes formed. Maybe they formed together with the galaxy. This is something that people look for an explanation of, but they are very interesting to look at. And of course, well, what's a black hole? A black hole is an object that is so dense and so massive that not even light can escape its gravitational pull. So you could, for example, make a black hole out of the sun, even of the Earth, if you squeeze the Earth into a small enough space. I don't know how small, probably smaller than a millimeter. If you squeezed all the mass of the Earth down into a very tiny ball, it would also become a very small black hole. And larger black holes form, like I said, when a star explodes, its outer envelope explodes and the inner core collapses into a black hole. And you have black holes at the centers of galaxies. But to think about black holes, kind of conventionally, you think about them as sucking, constantly sucking in matter. But that's actually not true. It's not that easy to fall into a black hole, and that's because you have momentum. So for the same reason, if we have an artificial satellite around the Earth and something goes wrong with the satellite, it goes offline, whatever, it breaks, it doesn't just fall to the Earth immediately. It carries on orbiting because it has momentum. And it only comes down once it's lost enough momentum from the friction of the atmosphere. That's when satellites come down. But if there's no friction, things just keep going around in a circle. And nature likes rings. So here's a famous example of a ring. This is Saturn. And the rings of Saturn are actually, this is the remains of a moon that's broken down. So it was a natural moon of Saturn, and it was broken apart by tidal forces. At least that's what we think. And you can see all the stuff that's left over from it just carries on orbiting in a ring. It's not falling down onto Saturn. It's going to carry on orbiting in a ring for quite a long time. And this would be the same for you if you were to fall into a black hole. More likely, you were going to spin in a disk around the black hole for a very long time. So that's what happens around black holes. Things spin around in something called the accretion disk, and on the very inside of the disk, stuff slows down enough to actually drop in. But because black holes are so massive, and because they actually distort space-time around it, if you were to look at this disk around the black hole, the disk itself would be distorted, and you would probably see something like this. And this was actually made famous by the movie Interstellar, where they used realistic simulations of what a disk around the black hole would look like. So you see, it looks like this is the front part of the disk, and this is the back part of the disk that's been kind of bent around by the gravity. So you see this weird shape. So this was science fiction. This was all science fiction until last year, people finally managed to make an actual image of a black hole. And this was done by a telescope called the Event Horizon Telescope. This was a network of very long baseline interferometry, like I explained earlier. You take telescopes across the world and you link them up. And this is where the telescopes were. So you could see there were truly, one was in Greenland, one was at the South Pole, and there were a bunch of in between here. And when you have baselines that long, you can get absolutely fantastic resolution. So the resolution here is about 1,000 times better than Hubble. It's good enough that you would be able to see an orange on the surface of the moon with this thing, if only the orange was emitting radio waves. And this thing was built to look at black holes. Its objective is to look at the supermassive black hole at the center of our galaxy and at nearby galaxies. And the first image they actually got was the image of a black hole at the center of MH7. And that's it here. You know, it looks a little bit blobby, of course, but this is, you know, this is like an extreme zoom. They're really looking into the center of that galaxy. And they're actually seeing this accretion disk around the black hole. Over here, you have simulations of what it should look like if you had even better resolution. But because the resolution is limited, they get this. But this is, you know, this is truly a staggering image. It's the first time anyone has seen a black hole, and people from Rhodes were quite closely involved in this result, at least 3 of them. And by the way, one thing I should point out, the orange reminds me. I keep showing you these radio images in orange. So radio waves aren't really orange. Radio waves are just radio waves. It would probably be more accurate to show things as black and white, as I said. You know, the images only indicate the intensity of the radio. But for some reason, we like to use orange. You know, it makes the images prettier. And maybe that's why they're talking about seeing an orange on the moon and not an apple on the moon or a pomegranate on the moon. I don't know, some kind of subconscious thing with radio astronomers and orange. Anyway, that's it for the black hole at the center of the galaxy. There's a very interesting problem in astronomy of where is the missing middle class, because we can kind of detect black holes that are the mass of the sun, and then there's a black hole that's 4 million times the mass of the sun at the center of our galaxy, and we don't really know many black holes in between. So there's some kind of cosmic austerity might be some kind of cosmic austerity at work that's eliminated this middle class of black holes, but we don't know, or maybe we just can't see them very well for some reason. But there is actually another black hole in this image, and this is a true monster. And you can see it here, this little smudge. It's not very impressive, so I'm going to show you another image which kind of highlights this. So this is another image made with MeerKAT. It's called the Deep 2 field. And the thing to realize here is that every dot in this image is a galaxy. Every single dot is a galaxy. And it's not a big patch of sky. Again, it's about 2 moons across. So, you know, that's how many galaxies there are if you just stare deep enough at a particular patch of sky. But another thing you might notice if you look closely at this image is that there is a certain pattern that seems to repeat itself. So if you look here, you've got a dot and a couple of lobes around it. And then here's another one. And then here's another one. Somebody's got their microphone open. Could you please check? And once you know how to look, once you know where to look, you actually realize that the sky is full of them. So you have this very repeating pattern in galaxies, and you kind of start wondering what that pattern is. And these, of course, are very distant galaxies, so we cannot see very much detail. But turns out we're lucky enough that there is one close enough. And it's a very famous object. It was actually discovered by Reber in 1937. You can see it in his maps. This little blob here, this is one of the brightest sources in the sky. It's called Cygnus A. It's a radio galaxy. And with a modern telescope, it actually looks something like this. And what it is, it's something fairly mundane. Well, it's one of the brightest radio sources in the sky. It's called Cygnus A because it's in the constellation of Cygnus, and radio sources are given letters. So it's the brightest source in Cygnus, so it's Cygnus A, first discovered by Grote Reber. And you would think if it's the brightest radio source in the sky, it must look pretty spectacular to optical astronomers as well, right? And actually no. So this is an overlay. In yellow, you can see an image from an optical telescope, and in red, the radio. So in yellow, in the optical, what you actually see is just a little galaxy. Absolutely nothing special about it. Just a little malformed galaxy, not terribly bright, nothing special. When you look in the radio, there's these things, huge, huge things, which are actually 400,000 light years across. So what's happening here? Well, what's happening is that something in this galaxy is shooting out jets of plasma at almost light speed. And that something is what we call an active galactic nucleus. And, well, shooting out jets of plasma at close to light speed sounds like exactly the sort of thing you would want to recreate in a kitchen. So I'm going to try to do that. I'll show you a little video I made this morning. So I wonder if this is going to play. Yeah, here we go. So I just took a syringe and filled it with some food coloring, and now I'm injecting it in the sink. And I would not recommend doing this experiment in Grahamstown because of the water shortage. So in Grahamstown, it will have to be a thought experiment. But in Cape Town, I could recreate it quite well. So the jets of plasma that shoot out of Cygnus A behave the same way as this jet of green water that's billowing out of my syringe. And that's because actually sort of the same thing is going on. So like I said, astrophysics is just normal physics except for very bad things, or very big things. So what happens here with the food coloring? You know, molecules of green food coloring, they shoot out of the syringe and they travel through the water until they smash into a water molecule. And that makes them slow down, and that makes the whole jet billow out. And exactly the same thing happens in a radio galaxy. You have these jets of plasma that shoot out. They shoot out into what we think of empty space, but empty space is not quite empty. There might be one atom per cubic centimeter, but if you travel for 200,000 light years, you're bound to hit something, even an empty space. So after 200,000 light years, this jet is hitting something in the intergalactic medium, and it billows out, just like this cloud here. But one thing you might notice is that it's not actually a perfect recreation of Cygnus A, but it is a pretty good recreation of another type of radio galaxy, which is here. And this is something that also has a South African connection. So way back in '74, Smirnov and Riley discovered that you actually have two types of radio galaxies. So you have one type that's bright in the middle and then kind of billows out into these lobes. And that's what I've recreated in my kitchen sink, I think. And then you've got the other type of radio galaxy, which is like Cygnus A, where you also have the jets billowing out. But at the end of the jets, you have these bright hot spots. And what's happening here is actually, if you can find the video of a bullet underwater, it's sort of the same thing. If you shoot a bullet underwater, I am not going to do this in my kitchen, and I'm not going to recommend it to anyone, but the bullet will create a shock front because it's traveling so fast. And that's what's happening here. So for some reason, whether because the jet is more powerful or the medium is more dense, the jets in Cygnus A, they cause a shock front, which makes for these hot spots that go in the radio. And for other galaxies, this doesn't happen, and the jets just kind of billow out in a more, in a calmer way. And this is called the Smirnov-Riley classification. So a South African named Bernie Smirnov did this for his PhD in Cambridge. And then afterwards, he went back to South Africa and he got involved in struggle politics, and he served in Mandela's first government. And later on, he became the first director of the South Africa project. So quite a famous name. So I'm talking about jets, but what causes the jets? That's a very interesting question. And since I've been talking about black holes, you might guess that it's a black hole. You would be correct. In fact, at the center of Cygnus A, there's a massive, massive, monstrous black hole that's about 2 billion solar masses. And you might say, okay, wait a minute. Black holes are supposed to suck things in. They're not supposed to shoot things out. Well, there's another ingredient involved. It's a magnetic field. And magnetic fields are kind of a joke. Well, no, they're very serious, but they're also a bit of an in-joke in astronomy because very few people actually understand what's going on with magnetic fields. So, for example, if you go to an astronomy talk and you fall asleep during the talk and you don't even know what people were talking about and you want to ask a question, it's fairly safe to get up and say, what about the magnetic field? Because most of the time people don't know what's going on with the magnetic field, and it makes you look intelligent. But what's happening with black holes is, with jets, is truly magnetic field driven. So you've got the accretion disk spinning into the black hole, and this accretion disk is magnetized, and it's twisting up the magnetic field into a funnel. And then somehow some of that plasma is kicked out, and it shoots out of the funnel and creates a jet. So to understand this, you really need to understand magnetic fields, and it is commonly thought that astrophysicists who deal with magnetic fields are at least twice as smart as normal astrophysicists. And then, of course, you get this headline. Funnily enough, this astrophysicist was also working on a COVID-19 response, but I don't think it was government sponsored. So I tried to recreate this experiment, but I didn't get very far. I also thought I would try to recreate this experiment, maybe by taking some magnets and putting them into a blender. But then I thought, no, this is, we've had enough astrophysicists with magnets headlines. So I just made a couple of smaller videos showing you what happens with magnets. And you can see that there's a lot of violence in these little things, right? So if you can imagine a black hole as a kind of a cosmic blender, and this is a super monstrous black hole which spins these magnets in, some of them will be kicked out and they will form these jets of plasma. And of course, as I said, some astrophysicists do work with magnetic fields. And another nice bonus of looking in the radio window is because in the radio, you can quite naturally measure polarization of signals. And polarization of radio tells you about magnetic fields. So here's some work by a Rhodes PhD student on the very same object, on Cygnus A. And this is actually showing you the magnetic field in the lobes of Cygnus A. So this is spectacular work, and this is one person. If you hear her talk, you can certainly ask what about the magnetic field, because she will tell you all about it. Unfortunately, she did not do this with MeerKAT. Cygnus A is an object in the northern sky. It's hard to see with MeerKAT. She did it with the Very Large Array. And you might have seen the Very Large Array in movies. This is not Lerato, this is Jodie Foster, and this is the movie Contact. And the dishes of the VLA are here in the background. So anyway, but the one thing I find remarkable about all this, right? It was Star Wars Day yesterday, May the 4th. And what I just explained to you, if you step back for a second, sounds like something straight out of Star Wars, right? It's a black hole that's a billion times the size of the sun, and it's shooting out jets of plasma almost at light speed, right? It's science fiction, but in fact, it's actually extremely common. If you look at this image again, it's a small patch of sky, and you can see, if you count carefully, you'd probably see at least 50 of these things. So actually, they are not special. They're like an impala. If you spot one, if you go to Kruger Park and you spot an impala, you're not going to be bragging to your friends that you spotted an impala, right? It's a regular thing. And the same thing for these monsters. Like, somehow they are regular. And I find that, to me, that's utterly fascinating. The fact that nature just naturally tends to put together black holes that are a billion times more massive than the sun and shoot out jets of plasma at close to light speed. That's kind of a normal and mundane thing, which, to me, I find that utterly wonderful. But sometimes we see even weirder things, even more special things, and that gets us to some recent news. So here's a picture of a galaxy in optical, and it's called the Jellyfish Galaxy. And you can guess why it's called the jellyfish, because it's got this long tail, which does make it look exactly like a jellyfish. And what's happening here is that galaxies are quite often found in clusters. And some of these clusters are very massive. So if you've got a massive cluster of galaxies, they will tend to interact gravitationally. They will be attracted to each other. You will see things like galaxies falling into the cluster. You will see all sorts of funny things. And there's a type of galaxy you will see called the jellyfish, which is, it's actually, so this galaxy is falling into the cluster. And as it falls, the gas from the galaxy is being stripped away. And you can see it here. So we were kind of, Patty, a research fellow here at Rhodes, she was quite interested in looking at one of these jellyfish galaxies for various reasons, which I won't get into. And this particular jellyfish happened to be here. This is an image from an older radio telescope in Australia. So this was an image of this patch of sky that we had. This little smudge, that's the jellyfish galaxy that Patty was interested in. And there was this annoying nuisance nearby, this bright radio galaxy, which we weren't particularly interested in because, as I told you on a previous slide, these things are pretty mundane and they are all over the place. But it's kind of annoying to have it in the image because it causes all sorts of problems when you're trying to detect faint things like the jellyfish. So this thing was purely a nuisance to us until Patty made an image, and then we saw this. And this is really remarkable, right? This you cannot explain in the kitchen. I've got my video in the corner here, right? Just to remind you what's going on. So to begin with, this looks like a sort of a normal galaxy, a normal radio galaxy. So you've got the black hole at the center here, and this black hole is shooting out jets. So this part you can recreate in your kitchen sink. If you take two syringes and you have two jets shooting opposite sides, you'll have a pretty close approximation of what's going on here. But then, for some reason, you know, all this plasma, and remember, it's still traveling close to light speed. For some reason, it decides to hang a right turn and then hang a left turn. And then suddenly you have these tendrils connecting the two lobes. Now that is truly bizarre, right? Imagine if you saw that in your sink. Imagine if you shot off two jets of food coloring in your sink in two opposite directions, and suddenly they sprouted tendrils and started connecting to each other. And to tell you the truth, we still have absolutely no idea what's going on here, but of course it has to do with the magnetic field. I mean, these sorts of structures can only be formed by the magnetic field, but the question is, where does this magnetic field come from here? Why is it so strong? And where do we get enough charged particles to fill up these arcs? But it's a fantastic thing to see, right? Because this is something we completely did not expect. And that to me, that's the best part about science, finding things that one doesn't expect. And there's another little thing in the same. This also, by the way, illustrates how better MeerKAT is than a competition, right? This was the previous best image of the subject looked like this. It was barely a blob. And then notice there's a little bullet-like thing on top here. And then with MeerKAT, we get this, right? The improvement is absolutely staggering. And if you look at this other object on top, the one that looks like a little speeding bullet, it looks like that. And this is also very cool, right? Because, I mean, it's May the 4th, so this is, to me, this is very clearly an Imperial Star Destroyer that's spinning out of control. Because it's very hard to explain otherwise. I mean, clearly it's a jet, so clearly it's another radio galaxy shooting out plasma. The question is, why is there only one jet? Why are we only seeing one? Well, possibly because this one is being shot towards us, and the other one is being shot away from us, and at the same time the galaxy is falling here to the left, so the jet is kind of billowing out behind it, and we don't see the one in the back. And so far here it looks like a normal jet, but look at all the stuff that's happening over here. Right? It breaks up into these fantastic wispy things, and someone just sent me a picture they took out of the car window of clouds, which looks remarkably similar to this. And you know, again, it makes the same point that astrophysics is kind of like normal physics, just at very large scales. This is, I don't know, also 500,000 light years across. And these structures look exactly like a certain kind of cloud. And that's probably, if you write out the physics of these structures, it will probably have the same equations that govern cloud formations up in the sky here. So anyway, I think that about takes me to my conclusions. I'm very bad at conclusions, so I'll just try to throw out what I can here. Well, firstly, the radio window, it's not cold and empty, but it reveals the real fireworks of the universe. My other conclusion is that astrophysicists aren't actually twice as smart as other physicists, but they do get to play with pretty pictures. MeerKAT is at least twice as good as any other telescope, but don't tell my American friends I said this or they'll kill me for it. And the take-home message is, do not stick magnets up your nose. And that's it. Thanks very much. I'll take questions now.
Thank you so much for that wonderful. I didn't expect to be quite so amused during a talk on something quite so esoteric as black holes and astrophysics, but there were a number of good moments there. I have to tell you that my son did stick a magnet up his nose, and that was quite a scary day. It cost a lot of money to get it out of his nose, but there you go. So that if we learned nothing else, hopefully we've learned that lesson. I love the fact that we heard about James Bond, Interstellar, Star Wars. You gave us lots of points of reference that even me with my limited understanding was able to connect to. We have, I know some people have had to leave, but those that are still there, I'm sure you may have some questions. And please, you can choose to either put your questions into the chat bar and Oleg will answer them, or if you put the letter M for microphone into the chat bar, then I can unmute your microphone and you can actually ask your question in person.